So what we're looking at here is the third part. I should have a 3 in brackets here. It should say circular motion and Newton's laws, part 3, I think. Is that right? Should say part 3? Okay. But this is on page 11 of your Unit 3 handout. What we're going to be looking at today is a couple of different applications of circular motion relating to Newton's laws of motion. So we're going to be looking at 2 additional applications today. The first one is something called artificial gravity. And artificial gravity can be created in a number of different ways. There is this device that people have created called a human centrifuge. And basically what a human centrifuge is something that rotates around very, very rapidly that you are inside of. I remember being a teenager. Me and Steve Badinsky would go to Klondike Days every year, or the Edmonton Exhibition, and I forget the name of the ride, but there was a ride that was basically a big drum. It was huge. It was probably about 30, 40 feet in diameter. And I'm going to just fix this, make it look a little better. And like, it's huge. And what would happen is you would get into this thing and you would stand on the floor with your back towards the wall. It was a big circular wall. And what would happen is this thing would start spinning along an axis, and it would start spinning and spinning and spinning, and it would go faster and faster and faster. And then what would happen is this floor, which I'm not drawing the whole floor because part of it's hidden by the front wall, but this floor, once it got moving very fast, the floor would drop out. It wouldn't just drop to the ground, but it was on some kind of a hydraulic system, so it would drop out. And the result was we were stuck against the walls. And what you could do is you could start maneuvering around. You could do this, you could wiggle around. It would be like you're crawling on the floor, actually. That was the sensation that you had. Of course, if I'm in that position and the thing slows down, and at some point I'm going to fall and I'm going to hurt myself. If you wanted to, and Steve Badinsky did this one time, the only way I can draw this if I draw it over here, is he stood up while this thing was spinning. And then we got in trouble when the ride stopped. But you could actually stand up and walk around. And a lot of people have a misconception here that you are being pulled by some force towards the outside. There is no force pulling you to the outside. What is happening is there is a force of the wall pushing against your feet, and you interpret that as artificial gravity. The bottom line here is this ride, if it's spinning in the direction I've indicated, my body at this point in time, if I'm standing there, is moving out towards you, but I don't get a chance to move in that direction because the wall moves in the way, actually. So I end up being stuck to the wall. It's a very, very difficult thing to understand. But this force is the centripetal force. It's the net force acting on my body. And I interpret that as a force due to gravity. Usually the person is seated, but sometimes they're standing up. So here is an example of a human centrifuge that they use for training, for medical training, for pilots. And this thing is going to end up rotating very, very rapidly around that central axis. And the result is that this person's feet will be pushed towards the center by that centripetal force, and they will feel weight. If everybody, the centripetal acceleration has a magnitude of 9.81 meters per second squared, I'm not talking about the gravitational field strength. I'm talking about the v squared over r. If the v squared over r has a value of 9.81 meters per second squared, and the person closed their eyes, other than feeling some air rushing around them, they would feel like they're standing on the surface of the Earth. If, on the other hand, the centripetal acceleration had a magnitude of 19.62, can somebody confirm that 19.6 is 9.81 times 2? Yeah, and Hunter, that's the name of the ride, the gravitron. Is it right, 19.62? Okay, so what we would say is, for this person's experience at an acceleration of 9.81, we say they are experiencing 1 g. At 19.62, we would say they are experiencing 2 g's. Now, just imagine that I have the same mass as you. And what you're going to do is give me a piggyback ride. You're going to support me on your back and shoulders, and you're going to walk around. Well, that force that you have to use your legs with to move around would be the force that you would experience under 2 g's. And when we talk about pilots pulling g's, we're talking about them experiencing a multiple number of gravitational fields. This is a cyclotron that you would be seated in. I'm not going to be able to do a very good job here of drawing this, but I'll go ahead and try it. You would be seated here so that your body is here, your legs are out in front of you, so you're seated like that. I think you get the idea. What happens when this thing spins around this axis is this whole piece here is on a pivot. So as it starts spinning faster and faster and faster, what happens is this whole thing rotates. And it's like I'm sitting in a chair. It's equivalent to being like this person who's apparently standing, except that this has you in a seated position. So if you were a pilot, you would be seating, and if you're a pilot sitting in a plane, I know, this is amazing. I can't believe my artistic integrity here. You were a pilot seated in this plane someplace here, and the plane goes through a circular arc, then that's where you pull g's. That's where you have to be able to withstand a certain number of g forces. They're used to train and screen astronauts and pilots. Sometimes pilots and astronauts need to be able to stay conscious for very high g's. And what happens is, in all of these cases, just like the ketchup in the ketchup bottle, the blood in this person's body is going to be forced, apparently forced, towards the outside to their feet. And if the blood drains from your head, you lose consciousness. And that's okay if you lose consciousness in one of these tests, but if you're flying a plane and you lose consciousness, then I hope you understand that that's a serious problem. So this is what they use to train pilots and astronauts. If you do experience high G's, you get what's called light loss. I had an opportunity to be in one of these things, and I got up to about 4 G's, and that was it. I was out. And light loss, all of a sudden, it's like something from a movie. Everything that you see, your field of vision gets smaller and smaller and smaller and smaller, until the only thing you can see is the little bit of light right in front of you, and then it's gone and you wake up feeling very nauseous. Higher G forces can result in permanent physiological damage. We don't really have time here with this 2-hour session, but when we get back, I will put together some videos showing some training. You can look on YouTube for a lot of different training for just Google into YouTube human centrifuges and you'll see the idea. So if the radius of the centrifuge is 4.5 meters, how fast does the edge of the centrifuge have to move if you're going to experience 1 g? Well, 1 g means 1 multiplied by a centripetal acceleration of 9.81 meters per second squared. In other words, everybody, we can use our formula for centripetal acceleration to calculate the speed. And you know, well, we'll do the frequency too. I think the frequency is less meaningful, but we can put in 9.81. This is going to equal v squared over 4.5 meters. So in order to find out, I just want to move this around and give myself a little bit more room. We're using a equals v squared over r. So in order to find out v, what we're doing is we're going to multiply a times r and take the square root. And the reason why I rearranged that formula is I don't really feel like writing it down again and again and again for each of these questions. So 9.81 times 4.5, and then we have to take the square root. So the person's moving at about 6.6 meters per second. If the person is experiencing 3 g's, what 3 g's means is 3 multiplied by 9.81 meters per second squared. So the centripetal acceleration is 29.43 meters per second squared. And again, to find the speed, we're using this formula. This is a multiple calculation thing. Actually, we could have done this with our lists in the calculator. So I need to take that and multiply by the radius of 4.5, and then take the square root. That can't be right. I forgot to hit equals, or I didn't hit equals. And we take the square root, and you get 11.5 meters per second. So I'm going to give everybody a minute here to calculate the answers to C and D. Then we'll talk about the frequency. We can customize that formula. We created the speed equals the square root of AR even more by just putting in the number of G's, and I'm not sure why I wrote 3. The number of G's times R. So if we take 5 times 9.81 times the radius and take the square root, we get our answer. So can I get some people to start typing some answers here for C, what you get, please? Okay, so I'm not going to go through the calculation here. I'm going to trust those 5 or 6 people that have calculated. You should get 14.9 meters per second. I think it was 14.86, a couple of people said. And can I get some answers for D? $21, yep. So 21 meters per second. Now we were also asked to find the frequency. I'm going to do only one frequency calculation for the 10G one. In order to find the frequency, you have to take the reciprocal of the period. But the only way to find the period is to use V equals 2 pi r over T. So we're going to have to use this formula first to find the period, and then we're going to use this formula second to find the frequency. And again, I only feel as though we need to do this with one of these. I can take the 21 meters per second. I'm going to leave out the units. You know, again, I shouldn't even need to say it, that if this is some written work you're doing, you need to include units. The radius is 4.5 divided by the period. So I would like everybody, please, to calculate the period for me. I hope most of you just know exactly what to do here to find the period with these numbers, but if you don't, you can cross multiply. And Miriam, can you tell us what you're going to get? I would like Miriam to respond as well, please. I'm just going to start picking on individual students. Not picking on them. That didn't come out right. I'm going to start choosing different students. So let us know when you're done the calculation, Miriam, if you get the same thing.
I kind of fell behind because I had to step out, so I don't have it quite yet.
Oh, okay. Do you need me to back up to anything, Miriam?
Just a little to the top to get.
Like that? So all we're doing right now is we are calculating the period from this formula. So we're not worried about the calculating the frequency just yet. We're taking our answer of 21 meters per second and putting it in for V, and that's equal to 2 pi r over T. So to calculate T, you're going to have to take 2 times pi times 4.5 and divide by 21. Other people can start chiming in here too. I just, yeah, 1.346, so you get that. I'm assuming other people are getting it. So the period is 1.346 seconds. That doesn't seem like a very small period. Like, it doesn't seem like you're going that fast. But this is a pretty big circle. The radius is 4.5 meters. So I don't know, it's hard for you to visualize probably, but if you run around in a circle that's 4.5 meters in radius, so 9 meters in diameter, you're moving around once every 1.3 seconds. The frequency is the reciprocal of that. Frequency is reciprocal of period, so we end up with 1 over 1.346, and that's going to give us units of per second, which we write as hertz. Brianna, can you let us know what you get for the frequency? .743. I would say that that's reasonable. Does anybody else get 0.74 hertz? Okay, so we're good. Let's move on now. Let's take a look at the next example dealing with artificial gravity. Artificial gravity can also be used in deep space to produce gravitational fields or apparent gravitational fields. This image is from an old movie called 2001. And in the movie there's this large satellite. It's 75 meters in diameter and it rotates around the central axis. And the idea is, this thing is huge. I think if you've seen the movie Elysium, I think in the movie Elysium they have the same concept. And what you basically have is a huge ring. And you stand here, that's you, or some animal of some sort. But you stand on this thing, and it's rotating, and it's so big that you're not even aware you're on the inside of a curve because it's so big and it seems flat, and you're able to walk around on this thing. So it's the same thing as a human centrifuge, except that it's a satellite in orbit rotating. At what rate must it rotate? Rate means frequency. At what rate must it rotate so that you experience a centripetal acceleration of 1g? Well, what I'm going to choose to do here is use this formula for acceleration. It's not a formula that I really care to use most of the time, but in this case, if we know the acceleration, we can use it to find the period directly. Once we know the period, we can take the reciprocal to find the frequency. So 1g is 9.81. I have 9.81 equals 4 times pi squared times 75 over t squared. If I cross multiply, I get 9.81 t squared equals 4 pi squared times 75. Thank you, Evan. Thanks for catching that before I went any further. I'm back to making that mistake I made 2 days ago. The diameter is 75 meters. I'm really glad you caught that. The diameter is 75 meters. So the radius will be 75 meters divided by 2, which is 37.5. Okay, good, thank you. So I need to put 37.5 in here. So when I cross multiply, I get 9.81 t squared equals 4 pi squared times 37.5. We can divide both sides by 9.81 to get t squared equals 4 pi squared times 37.5 divided by 9.81. And that will give us t squared, so we can go ahead and calculate that number. Four pi squared multiplied by the radius of 37.5, and then we want to divide by 9.81. Double check my numbers, they look good. So t squared is 150.9. Do you get that number before you square root it? Okay, good, thank you. That means that t equals the square root of that. We're going to take the square root of both sides. So the square root of the answer is going to be, what do we get? 12.28 seconds. So it takes 12.28 seconds to go around once. The frequency is the reciprocal of the period. Period and frequency are reciprocals of each other, so we need to take 1 divided by that 12.28 seconds. And again, when you divide by seconds, you get units of per second, which are hertz. So the period is a the frequency is a very, very tiny number. It's only 0.081 hertz. Remember that frequency, which is what we have here, is how many times it goes around in a second. Well, since it takes 12.2 seconds to go around once, it doesn't even go around a full revolution per second. Are you getting the same number? Okay. All right. There's one other thing we're going to look at today, which is friction for cars driving around curves on a highway. You've got a car driving around a curve on the highway. There must be a force pulling it towards the center, and that force is a force of friction between the tires and the road. If you've ever been in a car and you're driving too fast and it's icy out and you go into a curve but don't go into the curve because you end up just traveling straight, that's because there's not enough friction to pull you towards the center of the curve. I know that it's hard to visualize, but when you look down on a car that is traveling in a circular curve, there is a force acting on the car in that direction. By turning the steering wheel to the left, you create a pulling frictional force to your left. Assuming you're traveling in this direction, that force is to your left, so the centripetal force is here, but what's causing it is the force of friction. And that also is the net force. So when you have a car moving around a circular path, the net force is the centripetal force, and the centripetal force is caused by friction. So in all of these cases we're going to look at, the force of friction causes or is the centripetal force, which is the net force. These are all just different ways of describing what's going on. So assume the coefficient of friction between the tires of a car and the road is 0.75, and that's typical for regular driving conditions. The road is traveling around a circular curve of radius 60 meters. What's the force of friction? Well, the force of friction is, we're back to the previous unit, mu times the normal force. And I'm assuming that this vehicle is driving on a level road. It doesn't have a banking to it, which means that the normal force and the gravitational force are the same. This is what we had to do in the last unit whenever we had a question where we wanted to find the force of friction. We had to determine first how to find the normal force. Wrong? Did I do something wrong here, Liam? Oh, yeah. Yeah, you're right. They're not equal. The absolute values are equal. The magnitudes are equal. I got a little sloppy there. You're right. Thank you. So what we're going to do here is to calculate the magnitude of the force of friction. We're going to take mu times m times g. And that's a calculation I don't even think we need to write down. We can just do that on our calculator. We're going to take 0.75 times 1800 times 9.81. We'll get the force of friction. I just want to know, does anybody else get 13.243 kilonewtons or 13,243.5 newtons? I'm going to round that. No, let's leave it alone. Let's leave it exactly at what it is. (13,243.5). So that's the force of friction. Now, before we go on, you need to understand something very important about this. That's the force of friction between the tires or the car and the road, no matter how fast I'm going. That's the force of friction. If I go faster, nothing changes. If I go in a straight line or in a curve, nothing changes. And now what we're going to do is we're going to determine the centripetal force needed to move the car in this circular path. And I'll remind you what the radius is here for those of you just looking on the screen. The radius is 16 meters. The radius is 16 meters. 60 or 16? 60. The radius is 60 meters, and the mass of the car is 1,800 kilograms. This is a case, everybody, where we're going to do 6 calculations, but my God, I don't want to have to do 6 separate sets of calculations. So how is it we determine centripetal force? What I'm about to show you is what you would need to have on a written exam or a written assignment. You say that the centripetal force is equal to the net force. And that is true. I don't need absolute value signs in this particular case because they are the same force. They are literally the same force. But I'm just going to continue by saying that this is MA, and I'm not going to worry about direction in any of my further calculations. And A is V squared over R. So I end up developing this formula, FC equals mv squared over r. And this is the formula we're going to use. And we're going to go through and use our calculator like we did yesterday by using the list features of our calculator. First thing I would like everybody to do is oh, you know what? This is good. If you go to your lists right now, go stat edit, they're probably populated, aren't they? From yesterday? How many of you have numbers in your lists from yesterday? Oh, you cleared yours? Okay, so to clear them, everybody, go to your memory management menu, which is where you go to reset your calculator. It's second plus. And if you go to second plus, there's an option that says clear all lists. Choose that and hit enter. So now what I would like everybody to do, and do your best to follow along here, is in L1, enter your speeds, 55, 60, 65, actually, wait a minute, 55, 60, then it jumps to 70, okay. Don't know why I don't have a 65, but that's okay. I have 55, 60, 70, 75, 80, and 85. Just double check here, are your numbers the same as mine? You don't have a 65? Okay. So I'm going to quit out of here and move my calculator over so you can see the formula that I've highlighted. We need to take V squared over R and multiply by the mass. But V has to be in meters per second. So my first step is to take list 1 and divide by 3.6, which will give me meters per second, and I'm going to store that in list 2. I mean, I could store it in list 1, but that's okay. In other words, I could replace list 1. If I were to go into my lists now, I would see the speeds in meters per second in list 2. There they are. Okay, now I need to take mv squared over r. This is really easy when you figure out this list thing. mv squared over r will be the mass, 1800 times list 2, which is where my speeds in meters per second are, squared, I have to square that, divided by the radius, which is 60. And I want to store them in a list so that I can see what the values are. So I'm going to store them in list 3. So that's mv squared over r stored in list 3. By the way, you can see what they are by scrolling around on your home screen, but if you go stat edit, you can see what they are. Is everybody getting the same set of numbers? Okay, so I'm not going to write these down. At 55 kilometers per hour, you need 7,002 newtons. These are the forces. These are the needed forces. They are the necessary forces. All right? Let me ask you a question. Will the car be able to navigate the turn at 55 kilometers per hour? Well, what's the force of friction? The force of friction is 13,243.5 newtons. At 55 kilometers per hour, you need 7,002 newtons. Will the car safely curve around the highway? Yes. Will the car be able to successfully travel at 85 kilometers per hour? The force of friction, I'll write down so you can see it on the screen. The force of friction is 13,243.5. Is it successful at 55 kilometers per hour? Yes, because the force of friction is more, maybe if you're a good driver. Actually, no. It doesn't matter how good of a driver you are. If you're a good driver, you're not traveling at 85 kilometers per hour. You cannot just say, I'm a really good driver, so the laws of physics don't apply. I know you're kind of being facetious there, Evan, but I want to be serious about it for a second. Since this force needed to navigate the curve is more than the force of friction is able to provide, you will not be able to stay on the track. You won't be able to stay on the track at 85, you won't be able to stay on the track at 80, and you will be able to stay on the track at 75 because the force required at 75 is smaller than the force due to friction. Does that make sense, you guys? All right. So now the question is, and this is the kind of question that I would normally ask, what's the maximum speed that the car could travel with? Now, Liam, yesterday we had a conversation about, I think it was 35 newtons and we were using 34.999. We don't take that approach here. What we do is we say that that centripetal net force can only be as big as the force due to friction. In fact, what I've said here is where we started. The centripetal force is the force of friction. We don't need absolute value signs here, but I'm going to put them anyway. We don't need them because those two forces are the same. How do we calculate the centripetal force? It's mass times centripetal acceleration, because it's net force. And the force of friction is mu times the normal force. But the normal force is m times g. I would like everybody to look at this formula that we've developed very carefully. And I'm going to turn it into a little math class for 30 seconds. Can we algebraically simplify that formula? We can divide both sides by m. Remove m, yeah, divide by m. So what we end up with is the centripetal acceleration, which by the way is v squared over r, I won't do that. I'll do this in steps. So we cancel the m's and get AC, the centripetal acceleration is mu g, but this is v squared over r. And we can rearrange this now and get v equals r mu g, but we have to take the square root. And by the way, you could have just said mv squared over r equals mu mg. I mean, a lot of you will start here in this type of question. But you would have to explain it on an exam or a question on an assignment. So we put the numbers in. 60 times 0.75 times 9.81 and then we take the square root of the answer. Does anybody else get 21 meters per second? Okay, so we would say 21 meters per second. If you wanted to know kilometers per hour, we could multiply by 3.6 and get 76 kilometers per hour rounded to the nearest kilometer per hour. Don't psych yourself out here and say, well, if we round to 76, that's too fast. You just round your answer using the rules for how you round the answer. This is a very interesting result here, that the velocity that's... By the way, imagine that you had all of these details and you were driving. Would it be safe to drive at 75? No. I'm not saying this is perfectly safe. I'm saying if everything stays the same, you could technically do it. But it's an interesting result because that maximum speed has nothing to do with the mass. It doesn't matter what vehicle you're driving. Well, it does because the tires matter, but the tires would change the coefficient of friction. There are some questions here related to forces of friction and related to artificial gravity.